Hello, my name is Joseph Stranges, and I'm going to give a presentation on copper-2 directed synthesis of neutral heteroditopic 2-rotaxane ion pair host systems incorporating hydrogen and halogen bonding anion binding cavities. So this is a paper that was researched with Asha Brown et al., and I'm going to start by beginning by speaking about what a rotaxane molecule is. These are mechanically interlocked structures that consist of two parts. The first is a linear component in the shape of an axle that you could see in blue on the right. The second piece is a macrocycle that you could see in green. The macrocycles twirl around the axle, and if they're not fixed in one spot, they'll actually rotate around the axle to switch certain signals on and off, which is very interesting about rotaxanes. They're held together by strong hydrogen bonding interactions. And what's so special about these rotaxanes in particular is that they are neutral and have two sites for ions to bind. We're going to call them nH2rip host systems throughout the presentation to stand for neutral heteroditopic 2-rotaxane ion pair host systems. And these rotaxanes are synthesized by methods of threading, clipping, slipping, and active template methods, which is what we'll focus on in this research. Taking a closer look at the design of the nH2rip host systems, you can see that there are two distinct binding cavities for the ions. We have an anion and a cation in the picture. The macrocycle is this key chain loop in blue that's twirling around, and we can see the hydrogen bonding characteristics by identifying the NH groups along it. The red piece is our axle component, and we're going to have two different types of axles we'll make our rotaxanes with. The first has hydrogen bonding activity, which is 2,2 bipyridyl 4,4 bis amide axle. The second axle is 4-iodo-pyridyl 2,6-dicarbonyl pyridine, which has the halogen bonding. So we're going to take a look at two different rotaxane designs and put them side by side. These two different rotaxanes will be synthesized the same way. We're going to use a copper-directed synthesis, which begins when we make our macrocycle. So our macrocycle is formed in place when reacting with a few reagents. The diethylene triamide is adding a few more amine groups to close the ring, and the introduction of the copper ion is directing the electronegative nitrogen heads towards that positive charge ion in the center, kind of giving it a little bit more shape, a little bit more rigidity in its structure, while also making the cycle positive 2 charge overall. Any important step in making a rotaxane is synthesizing a pseudo-rotaxane as an intermediate step. So we're using our same copper 2 template from earlier, and we're reacting that macrocycle 2 times. One is with our hydrogen bonding axle, the second is with our halogen binding axle at the bottom. The copper is kind of reacting as a template here to direct the things to go together that we want. It's allowing for the formation of our pseudo-rotaxanes on the right. The axle is in red and the macrocycle in blue. So this is a very early on picture of what our molecules will look like. So with our two different axles, we'll synthesize two different rotaxanes. With hydrogen bonding activity, we'll synthesize 2-rotaxane 8-ZnClO4-2. We're going to add a little bit more bulk to our axle to prevent the macrocycle from leaving. And when we react everything together, we start to see more of a traditional rotaxane shape. On the left, we see a macrocycle in blue and our axle in orange. The problem with this picture right now is our macrocycle is going to keep twirling around that axle, in turn switching certain signals on and off that we don't want. So we're going to introduce the zinc ion to hold our macrocycle in the middle, It won't go anywhere. And we see lots of bulky groups on the end to make sure that our macrocycle stays on that axle. We'll synthesize 2 rotaxanes here. We're going to synthesize 14-ZN ClO42 and 15-ZN ClO42. This is with the presence of our halogen binding axle. And our rotaxanes are synthesized in a very similar fashion. However, we see a different axle present and a much longer axle chain for 14 and 15. We get a little bit more presence of ZN-ClO4 14, but we'll kind of group them together when taking a look at results. We'll take a look at the H-NMR spectra of the metal-free 2-rotaxane 8. We'll take a look at the macrocycle, the metal-free 2-rotaxane 8 itself, and the non-interlocked axle. The metal-free means that there is no zinc ion in this analysis. So we see some important shifts in the F and G protons. The protons 2 and 3 are shifting downfield as well. If we take a look at where these protons are exactly, F and G are aromatic protons on the macrocycle itself. 2 and 3 protons are on the base where that macrocycle is located. They're shifting from mutual shielding of the aromatic pi systems, so those double bonds are shielding away, and stabilizing donor-acceptor interactions. For our metal-free 2-rotaxane 14, we see similar shifts in the same protons. F and G are shifting a little bit more up, which is suggesting similar intercomponent aromatic donor-acceptor interactions in this rotaxane as well. We're going to take a look at the zinc complex rotaxanes. Our force spectra shows the metal-free 2-rotaxane 8 on the top. Below that is the metal complex rotaxane. The third spectra is the metal-free 2-rotaxane 14, and right below that is with zinc introduced. So in our analysis in the 8 sample, we see aromatic bipyridine protons 1 and 2 and I and J deshielded by zinc, explaining the shift downfield. In both 8 and 14, the macrocycle aromatic protons F and G are shifting due to the zinc locking the macrocycle in place. And what that's meaning is that pi electron cloud overlap is coming at play. Both 8 and 14 experience a reduction in their symmetry from C2V to CS from axial proton splitting, but both are consistent with an interlocked co-conformation, which is very important when taking a look at rotaxanes. That's what we want in their structure. Then lastly, we'll take a look at anion recognition over some stability constants. And there seems to be a selectivity for chloride and bromide ions over iodine and nitrate. When taking a look at the data, we have 8-ZN in the first column, 14-ZN in the second, and 15 on the last column. So we see that the values for Cl and Br are a little higher over NO3. So what's interesting here is the rotaxane has an overall selectivity for acetate ions, which is a little interesting considering that the structures tend to bind towards the chloride and the bromide anions. So we're going to take another look at an H-NMR spectra of 2-rotaxane 8-ZN-ClO42 in different titrations. So the rotaxane interacts with acetate ions through different binding modes, showing shifts in protons 1 and 1' a little bit more down. So these protons will move upfield in the presence of acetate and move downfield in the presence of halide ions. So with this being said, it's shifting in the way towards acetate. When taking a look at that for 14-ZN ClO42, we're taking a look at the same downfield shifts and proton signals 1', but also C. The stability data shows 14 and 15 rotaxanes show less discrimination between halide and nitrate ions compared to 8, meaning that they'll select them a little bit more in the hydrogen bonding component. And a preference for bromine and iodine binding was observed in both rotaxanes in these conditions, partly because of salvation factors. 14 and 15 have similar anion recognitions, suggesting that the halogen bonding plays a minor coulombic role in the structure. So while these rotaxanes favor different ions overall, I think it's very important to explain why it matters, because there exists plenty of non-interlocked ion pair receptors, but not all of them are neutral. Not all of them contain multiple binding sites. So being able to synthesize rotaxanes like this in research have been pretty rare. And having two different recognition sites can behave as like a shuttle for switching. So that macrocycle shifting up and down the axle will switch a few more signals on and off in both biological and environmental situations. And by having a good design for rotaxane, we can manipulate its function to be a little bit more in tune with what we're interested in. So thank you for listening to my presentation. I'm open to questions. Have a great one.